Hello everyone, it's my great pleasure to give you a short introduction into the simultaneous localization, or in short, SLAM problem. And I want to do this in relation to the photogrammetry activities that we have done in this course so far. So also relating the developments that happened in the SLAM community with respect to bundle adjustment, for example. But first of all, what is SLAM? SLAM stands for simultaneous localization and mapping. And it means localizing a robot or a sensor in an environment and at the same point in time building a map of the environment. So two very coupled problems. So let's have a look into the individual problems. Localization is a problem of estimating the position as well as the heading or the orientation of a robot or a sensor in an environment. And here typically you have a map of the environment. So something you can relate your sensor information to. So the result of the localization system is at every point in time an x, y, z coordinate and a yaw pitch roll angle, for example, if we live in the 3D world. Could also be just an x, y coordinate and a heading angle, the yaw, in case we are living in a 2D world. But often we do that in 3D, and it's all about estimating the position of my platform at every point in time. The mapping problem, in contrast to that, ignores the pose, or the pose is not relevant. The only goal is to come up with a map of the environment, so a representation of the scene. This map could be just a set of distinct points, of so-called landmarks in the environment, for example, extracted from SIFT features out of an image and then estimating where the point that created the SIFT feature is located in the 3D world. This would be a traditional feature-based or landmark-based representation. Other approaches take raw point clouds or work on dense point clouds, for example, if you have a 3D LiDAR scanner. Or there are grid-based representation or voxel representations where you represent the free and the occupied space in terms of voxels. So there's a variety of different map representations that you can choose, but the goal is to move a sensor through the environment or get sensor data in a passive fashion, to be more precise, and then turn that into a map. And mapping itself typically assumes we know the poses of the robot. So we know where the sensor was at every point in time, and it's all about building the 3D model of the environment. And SLAM now combines both tasks and aims at solving the localization and the mapping problem together. So we're basically building up a map of the environment and are localizing us in that map at the same point in time. And that's what we typically refer to as SLAM. So there was another term, CML, concurrent mapping and localization, which was coined around the time when also SLAM was coined, but SLAM was the kind of cooler term, and so the community stuck with SLAM in the end. So SLAM, again, is a term that has been established in the robotics community in the end of the 80s or beginning of the 90s, doing one of those workshops talking about how to build maps of the environment with mobile platforms. And it's a term that stems from the robotics community. And it's typically also used in the robotics context, especially then when we refer to the a platform, a vehicle, a mobile robot that moves through the environment. And we are often less interested in just the raw sensor data. So we can typically assume that the sensor data is generated from a platform that moves through the environment. Why is this relevant? This is relevant because you can exploit the sequential information. So if you think in the terms of images, it's not just a random collection or a set of images. We typically get a sequence of images of a system that was moving through the environment. So we know that, for example, two images which have been taken close to each other in terms of time, so let's say 1 second, one image taken 1 second after another image, that they are typically also have been taken from a place which is not too far away. Basically, it depends only on the speed that my vehicle can take. So in SLAM, as in opposite to bundle adjustment, for example, we often explicitly exploit this sequential information. And the term SLAM is also used whatever sensors we're using. So we're not restricted to cameras. If it would be purely camera, some people use the term visual SLAM, for example. But quite often other sensors are used, such as LiDAR range scanners, RGBD cameras, so cameras which provide a regular image plus depth information, could also be radars or sonars. It basically depends on the application or your robotic systems that you're actually using. So whatever sensors they are, we can exploit that. We also have means for exploiting, for example, the locomotion of the platform. So if we know how the platform moves through the environment, what kind of drive it has, then we can actually exploit that. So for example, if we have a car, the car doesn't move sideways instantaneously. Same holds for an airplane. So this is information from the locomotion of those systems that we typically exploit in the context of the simultaneous localization and mapping problem, because we are treating that as a whole, also taking into account the platform that was used to actually generate the data and exploit the capabilities or the constraints that those platforms have in our state estimation problem. So again, state estimation, or SLAM, stands for simultaneously build a map of the environment and localize yourself in that map using arbitrary set of sensors, being able to exploit the motion models of our platform. There can be different environment representations there as an output, landmark-based representation, volumetric, maybe even topological representations. And so there's a large variety of different mapping techniques that are one component of a SLAM system. Furthermore, we are often interested in online approaches in SLAM because we typically want to build a robot that navigates autonomously. And even if the platform doesn't know where it is, in order to navigate autonomously, we need to build the map on the fly while navigating. So at every point in time, we need to have a good estimate of the map based on the observations we've seen so far and the pose estimate of the platform. And so this is different to a lot of activities, for example, in the context of bundle adjustment, where we collect those images and then later on build a map of the environment based on that data. So online plays a much more important role in most SLAM systems because they are designed to be operated on a mobile robot while the robot is moving through the environment. So we can actually directly compare bundle adjustment here and SLAM. I mean, they are very related problems and address a very, very similar problem, but they're kind of slightly different flavors that are out there. So in bundle adjustment, we typically only consider images as our observations. I mean, we may add IMU GPS information to our mapping tasks, but most of the time when we talk about bundle adjustment, we refer to a purely image-based approach. We also consider typically sets of images. That means we just have a collection of images and want to work with this collection of images, not exploiting explicitly sequential information. Of course, if it runs in an online system, then we can take this sequential information into account, but the majority of bundle adjustment solvers which are out there don't take that into account explicitly. Also, given that we work on images and based on features we have extracted from those images, we typically try to minimize the reprojection error. So the discrepancy between where I observe a point and where the point is mapped into a virtual camera, assuming the current configuration that I have is correct. So something that we have discussed in the bundle adjustment lecture here. And so it always tries to minimize this reprojection error in the image plane. So we are projecting a point back into a camera and see is the point actually mapped to the location where I see it. And we want to minimize this squared distance. This typically leads us to a least squares approach, mostly done in an offline fashion. So that's kind of what bundle adjustment is about, as we discussed it here in that course. SLAM, in contrast to that, is typically not restricted to images. So if we use the word SLAM, we can use different sensors, even combination of sensors, multimodal SLAM, taking multiple sensing modalities into account, for example. Often those SLAM systems exploit the nature that there was a system moving through the environment and then one image taken in a very short amount of time that has passed between two time steps, then that means those locations are typically nearby. And we can exploit this sequential nature in order to build better maps or kind of make assumptions about the motion of the platform during these points in time. We also use motion models typically, so take the motion capabilities of the platform into account in this modeling task, and we can build all different types of maps, volumetric ones, landmark-based one, point clouds, whatever it is. We are not restricted to, let's say, 3D points in the environment, which is typically the assumption that is done in the bundle adjustment approach. In terms of the solutions that are out there, bundle adjustment typically refers to as a standard least squares error minimization approach. In SLAM, that is not necessarily the case. There are definitely also least square solvers around, and these are by now also the most popular approaches, but there are also other techniques, for example, recursive-based filters, such as a Kalman filter or a particle filter, that can be used for solving the simultaneous localization and mapping problem. I mean, we can use those tools also for bundle adjustment, but if we use the term bundle adjustment, we typically refer to the task of using a least squares error minimization approach, minimizing the reprojection error. And SLAM systems are often online approaches, not always, but most of the approaches have an online spirit because we want to build a map while the robot is navigating, And in the end, we'll have the same or similar result than the offline approach, but only after the mapping task has been completed. But the goal of the online approaches is to have the state estimate available at every point in time during the process itself. So if you compare this, we can actually see that SLAM is a generalization of the bundle adjustment problem. So it is more general. You can plug in different types of sensors. The bundle adjustment problem is, so to say, a special case of the SLAM problem here. And there's also the reason why we make this generalization, this direction, and this is also some historical component to it. So SLAM is relatively new. So it started in the mid-80s by approaches from Smith, South, and Cheeseman, as well as Udall and White, which used probability theory in order to describe geometric relations relating landmarks or features that we have seen from sensors with the poses, and this has led to discussions on how to solve this problem. This was in the 86, where also the term SLAM was then coined, and then a lot of activities were ongoing up to proofs, and kind of from 2000 on there was a wide interest in the SLAM problem within the robotics community. And this is in stark contrast to the bundle adjustment approach, because bundle adjustment is much older. So bundle adjustment has been developed in the 1950s in the photogrammetry community, so clearly 35 years before people in robotics looked into that. Even you can argue that at that point in time there was no real robotics available, and that would probably be true. So bundle adjustment is a special case, but the reason is that it was developed very much earlier, and then has also been picked up by the computer vision community, also being more restricted to camera images, and the kind of robotic community was the last community to pick that up, formulating that in a more general way, but also exploiting capabilities that typically occur in robotics. And I want to also go a little bit back in time. If you look into the 1950s, we could just ask a few questions, such as what computers were available at that point in time? Were there computers at all? How has the error been computed? There was no automatic image processing, no digital cameras around. So images were taken on film or on glass panes, and then all the image processing as we use it today, feature extraction, identifying landmarks, was done simply by human operators. And a lot of calculations had been done by hand or using standard calculators, which can be a very painful process if you have to solve large linear systems. So especially if we take into account what the technique or the IT support, so to say, that was available in the 1950s and compare that to today, that lets you even appreciate the developments that happened in the photogrammetric community in the 1950s in the context of the bundle adjustment problem even much more. So it's a greater appreciation for the developments which happened that early in time, especially if you take into account which kind of resources were available at that point in time in order to develop the solutions that we are basically still using today. Of course, being optimized to our computers, being able to exploit certain patterns that we see in those matrices, but nevertheless, the grounds for solving the system in that way had been developed much earlier in the photogrammetric community. Okay, but enough of history. Let's dive into the SLAM problem and explain or motivate the SLAM problem a little bit, so that we then can later on in subsequent lectures dive into individual realizations of the simultaneous localization and mapping problem. So the SLAM problem is often referred to also a chicken or egg problem, because if we look to a mobile robot, we can say, okay, we need actually a map to localize us. So localization is easy given a map, and at the same point in time, if we know our poses, also mapping is easy. But the problem is if both things are unknown, if the map is unknown and the localization is unknown. If you have to solve both things at the same point in time, then it's more challenging. And you can also ask always there, what was there first? Was there first the map and then we computed the pose, or the other way around? But no, we have to do this actually simultaneously together in order to achieve a good solution. So to have a good map and to have a good pose estimate. And so the SLAM problem is actually a very relevant problem for autonomous systems, because you typically have an autonomous robot that should navigate through the environment and do tasks for you. Even if you think about your vacuum cleaner robot, for example, although in small environments and for the vacuum task where you basically need to cover the space, you can actually do a random walk and just randomly drive around. And if you drive long enough, you will have covered the space. This is basically the approach that the early vacuum cleaners used, and that was already quite successful, to be honest. But if you think about somewhat more advanced systems, somewhat more advanced tasks, it becomes clear that they need to have a map of the environment in order to appropriately plan tasks or actions or clean up things. Then a map is needed. And basically for all tasks where systematic behavior is needed, maps play an important role. So solving the online SLAM problem is a key component for building truly autonomous systems or robots, so whenever navigation plays an important role. Just as a few example applications where that can be relevant. So if you're at home, if you do vacuum cleaning, again, you can do this as random work, but if you want to have a more systematic cleaning or later on show a map where the system has cleaned, then you need a map of the environment. If you perform lawn mowing and you want to have a systematic pattern how your lawn is mowed, which is typically the case, you will need to have a map or at least a good pose estimate of the environment. If you're in urban environments, thinking about autonomous vehicles or self-driving cars, they need a map of the environment. And of course, they're typically provided with a priori built maps, but the system needs to be able to update those maps, maintain those maps, and also deal with situations when a part is not mapped yet. You still want to be able to navigate maybe in a little bit more conservative settings, but you want to solve the SLAM problem as well. Same holds for underwater systems. So especially in Australia, a lot of people look into underwater mapping of coral reefs, for example. There also simultaneous localization mapping is crucial in order to get your robots back, in order to know where the coral reefs are. There's no GPS underwater, so a lot of challenges are there that you have to deal with. Also, if you think about the exploration of underground environments, let it be mines, let it be catacombs where systems are in underground spaces and need to explore those spaces, build maps of the environment. Here, simultaneous localization and mapping plays an important role. And last but not least, also for space missions, the system needs to be able to build a map of the environment, localize it in this map in order to navigate to certain locations and in order to operate in an autonomous fashion. So SLAM applications play an important role, just as a few examples of systems that have to use a simultaneous localization and mapping system. And with this, I want to dive a little bit more into the problem. So what is it from a slightly more formal point of view? So what do we have and what do we want? So what we have in SLAM, we typically assume to have executed controls. So the system executed commands like go a meter forward, rotate by 30 degrees, and so on and so forth. And this is information that is valid in the form of controls, or sometimes we also use basically the odometry information as controls, although this is already a sensor reading if you look into this in details, but that is often more accurate than the control information. So it's kind of the feedback from the control information, so to say. And then there are real observations with our sensor. This can be a camera, this can be a LiDAR scanner, or whatever it is that you're using as your sensor observations. And we assume we have them as streams coming in. So the index here is basically a timestamp. So we have sensor observations from time point 1 to time point t. The same hold for the odometry commands, where UT is always the command which advances you to the next state. So U1 maps goes from the initial location to X1, and U2 maps goes from X1 to X2, and so on and so forth. And then what we want to estimate a map of the environment M. Again, this can be an arbitrary representations, features, 3D points, point clouds, photometric representation, topology, whatever it is, we refer to it as M as our map, and a sequence of positions. And we can see here that the positions, we start from x0 to xt. So x0 is basically my prior information, where I start. From there, everything starts, and the first observations I actually obtain from x1 to xt. So x0 is basically, can use it as my prior information that I want to have. And if you see this from a probabilistic point of view, that means we need to estimate the probability distribution over those two quantities given those quantities over here, which I can write in this following form. The probability distribution about the path of the platform and the map in the environment. This horizontal bar we read is given our observations and our control commands. And SLAM is basically addresses how to estimate this probability distribution or how to get the most likelihood estimate out of that. So what's the best map and the best estimate for my trajectory? It depends a bit on what you want to do with it later on, if you need the probability distribution or are interested in the probability distribution or just the most likely explanation given your data. Often we are interested in the probability distribution, but a lot of subsequent processes then just use whatever the best map that we have for reasoning or the best trajectory of the platform. So it depends a little bit on your system that you have. We can also formulate that as a graphical model in terms of what are the variables that are involved in here, what is known, what is unknown. So in this Bayes network that you can see over here, we have basically a sequence of positions. These are shown over here from xt minus 1, xt plus 1, and so on and so forth. We have the map of the environment, which consists of all the landmarks, or my grid map, or my volumetric representation, whatever it is. And you can read those arrows basically as influences. So if you read the influences, you say xt minus 1 influences xt. So that means x1 conveys some information about xt. That makes sense if you have a platform that moves through the environment and doesn't do random jumps. If you know where you're at time t minus 1, this kind of constrains where you can be at time t, basically limited on the maximum speed of your vehicle, for example. So it has some impact on this estimation. But also the odometry command, so what has been executed is an important information. So if you know that I'm here right now and I command go 1 meter forward with 1 meter per second, for example, I know that I will be somewhere over here at the next point in time. And this is something that I can exploit in here. And also the observations. So what impacts the observations? What impacts the observations is where are the landmarks, so what I'm observing, and where is the sensor located or my robot located. Both impact these observations. And here, those are the variables we want to estimate with these gray underlined boxes. And these are basically my knowns, my known parameters. And those Bayes networks are quite commonly used in order to illustrate probability distributions or independencies in probability distributions. So these are my unknowns and these are my observed variables, and based on those errors you can actually make certain inferences about which quantities are dependent or independent of each other, and you can also do inference in those graphical models. Although in SLAM we use those graphical models most of the time as a nice model that we use kind of as a mental model, but the underlying solutions is not done using standard graphical model solvers, so other techniques are typically used. I talked before a little bit about SLAM between online and offline SLAM. So instead of offline SLAM, we also often use the term full SLAM, where we want to estimate the full SLAM posterior. This led to the term full SLAM, which was the posterior that I actually shown over here. And then this is kind of the more direct relation to the bundle adjustment problem. In online SLAM, however, we are only interested, or most of the time only interested, in the current estimate. So where the platform right now on a map of the environment. Because this is more relevant for the navigation purposes. Of course, I can basically store somewhere on disk my previous poses where I'd been before, but in terms of the state estimation problem, I'm only interested in estimating the current position of the platform, because this is what impacts my navigation system and how I build the map of the environment. And this graphical model for online SLAM looks slightly different, so the whole structure is the same, but the unknowns are only those two variables. So I basically don't need to estimate, or I can ignore or marginalize out the variables that refer to the previous poses. And so you can also reformulate the online SLAM problem in relation to the full SLAM problem by saying the online SLAM problem is the probability distribution that basically marginalized out all the previous poses. So in terms of the marginalization rule, so that means you're not interested in all the previous poses. So you can say the online SLAM posterior is your offline SLAM posterior, but you're integrating out or marginalizing out all the previous poses. So you're basically integrating them away. And then there's a direct relation between the online SLAM and the offline SLAM problem. And all these marginalization steps, they typically happen in our recursive base filter estimate. So if you perform our recursive estimation processes, basically in every iteration, we solve one of those integrals and integrate that always the previous pose away. And that's the way how we achieve our online SLAM posterior. So basically, if we talk about base filtering, which is the next thing that we will be doing here, using a base filter for solving the SLAM problem, then we are typically only as interested in estimating the previous poses, and we are basically not updating and not interested in the previous poses anymore. So what do we typically have? We typically have a robot that moves through the environment, and again, SLAM is kind of a tricky problem because the landmark locations are impacted by the estimate about the pose, and the estimate about the pose is impacted by those landmark locations. So you have those correlations between the position of your platform and the landmark locations of the environment. So you start with the robot moving around, it estimates, sees those landmarks, so these are landmarks in the environment, and the circles are now used to represent the uncertainties that we have. Then the platform moves through the environment and its uncertainty actually increases. It observes new landmarks. Then, of course, the uncertainty of those landmarks, at least in a global frame, are larger than those over here because the system had a larger post uncertainty as here the initial uncertainty, and as a result of this, the positions of those landmarks in the robot system are more unknown. So the robot continues, takes more observations, and at that point in time it reobserves an observation so it can constrain and kind of reduce the uncertainty of those landmarks. So while you're moving through the environment, you obtain your information and you correlate the uncertainty about the landmark location and the uncertainty about the robot's pose. And so and once you come back and reobserve landmarks, especially if you kind of close a loop, how we called it, then you can dramatically reduce the uncertainty in your estimate about the landmarks as well as the position of the platform. So you can see here, although this wasn't really a loop closure or what we call a loop closure, just a reobservation of a landmark, you can see how the uncertainties of the involved estimates actually slightly shrink. Also this one over here, based on the correlation between the map estimates, so the location of the landmarks, and the positions of your platform. What makes SLAM also very tricky is not necessarily the underlying state estimation problem, for which we have tools to actually do that, but one of the key factors is the so-called unknown data cessation, or unknown correspondences. That means quite often we have a pretty good estimate what we are actually seeing, but not all the time. So data cessation is basically a link between what we see in our observations and what we have stored in our map. So if I see something in my observation, can I say, oh, this is actually this element in my map. So this is what we call data cessation. And you can see this, assuming we have 3 landmarks in the environment which look like this, and the robot currently observes 2, and observes those 2 green with the green dots over here. So depending on the position of the platform, those 2 observations could be created by those 2 landmarks or by those 2 landmarks. It basically depends where we are. And if you need to estimate the correspondences, and let's say those landmarks look very much alike, this is a tricky problem. And it's actually the case that the pose uncertainty that the robot has, or that we have about the sensor location, impacts the data cessation that we are doing. So if we want to reason about all potential data cessations, this is it gets very quickly out of control because the number of possible data cessations are so large, and they are furthermore affected by the robot's uncertainty. And the problem with those data cessations is if I make a wrong data cessation, then this can have very bad consequences for my state estimation problems, and will typically lead to a divergence of my filter or in getting wrong estimates in there, because I basically have an outlier in my correspondences which lead to wrong updates of my filter, and this can again have very catastrophic consequences if I make a mistake in here. This was similar to the bundle adjustment problem, where you would use things like robust kernels, for example, in order to weigh down the effect of outliers in your data cessation. It's something you would need to do in SLAM as well. Again, it's a very, very similar problem because you have this unknown data cessation here. Traditionally, in the SLAM literature, we see 3 types of different algorithms which are used, or family of algorithms that are used. So the kind of base filter, group of base filters, and kind of the full least squares problem. So Kalman filters and particle filters as two examples which have been frequently used for the recursive state estimation, and I kind of this Kalman filter group here also includes in my notation things like the information filter, which basically performs Kalman filtering in the information space. So this all belongs to the group of, let's say, Kalman filters and friends. We have our particle filters around, and we have least squares solvers in order to solve the SLAM problem, for example. One thing that we're looking into will be EKF SLAM, which is a Kalman filter-based realization of the simultaneous localization and mapping problem. So a prominent example for this particle filter-based approaches is FastSLAM by Mike Montemallo and colleagues, or for example GMapping developed by Giorgio Grassetti and colleagues. These are elements of this particle filter-based approaches which are very popular in the community. Or in terms of least squares approaches, something we call graph-based SLAM, post-graph-based SLAM, or SLAM graphs, as well as the bundle adjustment problem. They would belong to this class of paradigms which I would use in order to solve the underlying estimation problem. If you kind of link that back to our graphical model, so that I had about the online SLAM problem, then we can actually see that for estimating the probability distribution about my variables, one, the poses, if you look to the local kind of surrounding of that estimate, so what are the variables which impact this variable? So this is the pose at time t, this is impacted by the pose at the previous point in time, and the control command. And for the observations, we have the observation is impacted by the position of the platform and the map of the environment. These quantities here and here is basically something that we know as our motion model as well as our observation model that we also used in the formulation of the recursive base filter. So what we have in here, the motion model or transition model, basically describes how the system evolves from one state to the next state under a control command and assuming uncertainty in the motion execution. And my observation model tells me how likely it is to get an observation or what I'm expecting to observe given the map of the environment and the position of the platform, and how does that relate to what I'm actually observing. So the motion model, so this part over here, is something that we typically refer to as the probability distribution about my new pose, given I know where I was before my old pose and my control command. So given I'm standing here, given I'm going forward with 50 centimeters per second for 1 second, so somewhere over here, then it's a probability about my current location. So it will be somewhere located here in this area. This is what the motion model tells me. And this can be a Gaussian model. That's something that we typically use within the context of the Kalman filter, for example, or that is also the kind of standard thing that you would use for a graph-based SLAM if you go for a standard least squares approach. But we can also have non-Gaussian models in here, such as this banana-shaped model in a sampled form or in a grid form, then requiring other underlying state estimation techniques in order to get that right here. And the second part was the observation model. This is basically the distribution about my observation given my pose and my, let's say, map built so far. So the map would should actually sit in here, but often you describe it just in this form because this X is often used as the whole state, and in SLAM your state vector, but kind of in our mental notation you may want to add an M over here, or the map built so far, depending if that makes it easier for you. And how are those models, could those models look like if we have, for example, a range bearing sensor, so a sensor which tells us the orientation of my platform with respect to, so in which direction I'm actually observing a landmark and how far it is away. This can be a simple Gaussian model, but we also sometimes explore non-Gaussian models where we have models that kind of look like this. This is here the raycast model for laser scanner, and then this needs to be taken into account differently, and it depends on the state estimation approach that you're using if you need to use this Gaussian model or can take into account non-Gaussian models in your state estimation problems. And based on the paradigm you're using, you need to choose one or the other. So the next step to do, if we go for EKF SLAM, we would stay here in this Gaussian world and need to take Gaussian probability distributions in order to perform the state estimation with the Kalman filter and run an EKF-based SLAM system as an example. If we go for more advanced systems, then we may leave the Gaussian world and take non-Gaussian distributions into account in order to better represent the uncertainties that actually occur in the real world. But that, again, depends on the system that you're using to perform your state estimation. So to sum up, mapping is the task of building a map of the environment, a representation of the environment. And localization means estimating the robot's pose or the pose of my sensor. And SLAM does both tasks at the same point in time. So SLAM, which stands for simultaneous localization mapping, means we want to build a map of the environment and at the same time localize within that map. And this is the task that we want to tackle. We need to distinguish, again, full SLAM and online SLAM as one of kind of the key things to differentiate those two approaches. Once the online SLAM is more done using recursive-based filters, and the full SLAM is more done using graph-based SLAM approaches, although there are also online variants that may take into account least square error minimization or an approximation of this. And there's kind of a full zoo of algorithms which are out there that you can use, which are also sometimes sitting in between online SLAM, full SLAM, or anytime algorithms. So depending on the computational resources, you do more or less activities. But kind of if you want to break it down to a very simple classification, online and offline is probably a pretty good one. And then the three paradigms are also a pretty good separation or categorization of the underlying algorithms. If you again want to relate that back to the field of photogrammetry, also computer vision, we could describe bundle adjustment as full SLAM, using a camera as your main sensor, minimizing the reprojection error, not taking into account the platform's motion, and come up with a least square solution. So in this view, the bundle adjustment problem is a special case of the more general SLAM problem that we typically have. But as I put that into the historical context before, bundle adjustment was developed years or decades before the SLAM problem. So it was more constrained in their definition, which also depends on the resources and the capabilities that were available in the 1950s when bundle adjustment was developed. With this, I'm coming to an end. If you want to read a bit more, a general overview, I recommend the Springer Handbook on Robotics, 2nd edition, and there the chapter on localization mapping. You could start with the subsections 1 and 2. For those of you enrolled at the University of Bonn, you can access it via eCampus. For the others, it's not that easy to access this, so you probably need to buy the book or see if it's available online. But it is a kind of a good overview of the SLAM problem and basically explains also what I have explained here before and then dives even deeper. So with this, thank you very much for your attention, and I hope you have an idea what SLAM is and how it actually relates to approaches which have been there previously, such as bundle adjustment. So thank you very much.